Today, I'm going to talk about 800 gigabit. 800 gigabit is the fastest speed we now see in mainstream R&D, validation, and even deployment. Of course, at VIAVI, we already have projects underway working at 1.6 terabit technology, but this is a little bit further ahead. Today, we see the majority of our customers and the ecosystem diving into 800 gig technology. And today we want to talk about this and help understand the different challenges as we move from chips to systems. So today's agenda, I'll first talk about the group we are in with the VIAVI NSE. We'll then talk about the 800 gig ecosystem today, the market we exist in and their needs. We'll work through chips to systems, what the different needs are across that different part ecosystem, and the relative timing we need to deliver successful products. We'll look at the key challenges. Each of those different segments has different needs as the products develop, and it's important that you understand the different challenges and test and measurement needs as you evolve and develop those products. And then we'll finally finish with a summary. There will be opportunities for Q&A, and so please use the chat facilities to forward any questions you have to my colleague Kenneth. We will be leaving time at the end for a Q&A session. So as we go through the presentation, please keep those valuable questions and let Kenneth know, and we'll make sure we'll get around to answering them either immediately at the end of this presentation or later on via email. But we very much want to hear from you and help work with you to solve your problems. VIAVI NSE, well, as we heard from Kenneth's video, we're 100 years old. And this really means a lot of experience, but a lot of experience with depth and breadth. VIAVI NSE works across many industries and many technologies. In the lab group, which I am part of, we cover many technologies, including wireless, PCIe, and optical. And this broad technology helps us deliver products that are very complete, because in reality, technologies like 800 gig do not exist in isolation. They are required for wireless or cloud applications. They rely on photonic optical technology. All of these things need to come together to deliver successful products that help solve our customers' needs. And the VIAVI NSE view of the whole ecosystem helps us understand the pieces to help deliver to you successful solutions. So now let's look at the market drivers for 800 gig. And I think the important thing to understand, it's drivers old and new. Transport and AI bandwidth demand continues to grow. Transport has been around for a long time. Since the earliest days of Ethernet, telcos and operators have driven those bandwidth needs, and we've seen enterprise customers as well. But what's really beginning to change things as we transition from 400 gig to 800 gig is the bigger and bigger impact of AI and machine learning. They now are very much setting the pace and the demands for bandwidth and latency in the latest 800 gig wave. 400 gig is already very successful. Millions of 400 gig ports have already been deployed, and they offer a wide range of capabilities. Everything from short reach DAT cables that might go a meter through to 80 kilometers or plus ZR optics. In fact, over many recent shows, VIAVI has demonstrated optics going out to 300 or 400 kilometers for 400 gig, working with our VIAVI test solutions, both in the module development, system validation, but also in the photonic domain as well. Continued development in photonics and standards is very, very important as well. Photonic technology, DSP and ASIC technology is really driving things as well. One of the biggest drivers for the 800 gig and beyond is the emergence of new switch silicon ASICs. The generation of 25 terabit moves to the generation of 50 terabit. This in turn drives faster and faster Ethernet needs. We see new optical form factors. These optical form factors, have to evolve with the speeds, but also thermal management to 30 watts plus for some of the coherent technology as well becomes very important as well. New technology, such as 100 gig SerDes, underpins much of the 800 gig wave today. Advanced DSP equalization and client data rates of 800 gig and even a path to 1.6 terabit, which VIAVI is working on now, really give us the capability to support the latest generation of 50 terabit switch silicon. All of these come together, all of them play an important part in our 800 gig ecosystem. Before we go much further, let's talk about what really is 800 gig, because with such things, many people can have different understandings depending where you are in the ecosystem. So I think the first thing to say, 800 gig is a port speed. OSFP 800 and QSFP DD 800 form factors, they allow 800 gigabits of second of bandwidth to be delivered on the front panel over an 8 by 112 gig electrical interface. Interconnects, everything from a 1 meter DAC cable to beyond 80 kilometers coherent ZR, can be supported in these plugs. So we have a port, and that port can deliver 800 gig of bandwidth. Now, of course, it can be Ethernet as an 800 gig stream, it can be 8 times 100 gig, it can be different rates, but the total rate of bandwidth you can get from that port is 800 gig, and it's very flexible. It can be 1 meter for interconnect within a switch cabinet. It can be 80 kilometers plus for transport DWM and DCI networks. But 800 gig is also an Ethernet rate. First, we saw the Ethernet Technology Consortium develop the 800 gig ETC. That had some success, but we're now seeing the IEEE 802.3DF work, and now that's quite a stable draft being deployed, developed and validated. And that backing by IEEE, the rigorous standards, is really now showing a lot more interest, and it's giving people the confidence to invest in the silicon and the systems for that 800 gig class Ethernet. So that's two big things, what 800 gig is. But actually, when we look at it on the grand scale of things, 800 gig may seem a lot of bandwidth, but it's a tiny fraction of what the latest generation of switch silicon can deliver. So that switch silicon is actually bounded and constrained by our 800 gig ports. This is why people today want to move from 400 gig to 800 gig, because they want to deliver that bandwidth the silicon can manage and switch and process in the most effective manner. And today, that is 800 gig. So it's a port speed supported by two flavors, OSFP, QSFP DD 800. It's interconnects from DAC cables to long-haul coherent optics. It's an Ethernet rate, and especially now with the standards of 802.3DF getting more and more crystallized, the confidence of people delivering it is growing, and people are really working hard on delivering projects, products, and systems. We at VIAVI like to think in terms of a complete ecosystem. We think that looking at things in isolation is not the most effective way, because the reality is products flow from chips to systems, and everything is tightly interconnected. You cannot build a modern switch or router or transport without ICs, with the chips, and without pluggable optical modules. So the VIAVI approach is to understand the flow and the technology needs at each side of the life cycle. The very leading edge, the tip of the spear, is the IC companies. This can include a wide variety of applications from PHY chips, switch silicons, network interface cards, AI chips. All of these tend to be the leading edge of things. They need to be tested and validated at the highest performance. And very, very important is the PHY layer, the lowest physical interconnect between the chips themselves, running at 800 gig at 112 gigabits per second. That becomes very, very critical. You also need to validate the IP. 800 gigabit is underpinned by lots of complex technology, including FEC and PCS and MAC layer. Without validation of that, that also means your chips are doomed to fail, and chips remain a huge investment. Typically today, to bring an 800 gig class chip to market is investment of millions of dollars. So it's very, very important, even at the early stages, you can test and validate that. The next big important step in the chips to systems ecosystem are optical modules and interconnect. So all Ethernet interconnect from DAC, copper cables and active cables through to pluggable coherent optics, all are a critical part of our 800 gig ecosystem. They bring together some ICs, DSPs, coherent ICs, and they need to be made sure that they work and interoperate with standards. Certainly with optical modules and cables, interoperability is key. That happens during the validation and production phase. Another big part that plays a huge role in 800 gig modules is management. Those modules need to be controlled and coordinated. So CMOS, the latest module management, plays a very important role in that, and having a good understanding of that CMOS in the modules and interconnect is critical. All of these things come together in complete systems, in those hardwares, those switches, those routers. It includes very, very large silicon. It includes lots of ports and plugs, QSFP, DD, OSFP. All of that must come together in the network equipment systems lab. They need to develop and work together. They need expertise in hardware and firmware integration, but all of this with an eye on the nanosecond precision stability people need. So multiple 112 gig lanes delivering bandwidth through ICs, over optical modules and DAC cables. All of that needs to happen, controlled by software, low-level software, but tuned to nanosecond accuracy. Very, very tight integration is the key to successful 800 gig network element delivery. Very, very challenging, all underpinned and that chips to modules to systems ecosystem. That's what leads to successful 800 gig products. We at VIAVI like to understand how that ecosystem comes together, and we look at this through flow diagrams. We look at the needs of the chip suppliers, the transponder and interconnect suppliers, the system providers, and the end users, so the service provider end users, ICPs. And what we do with every technology wave, we map out what the customers and the ecosystem needs at that time. So if we were to map out today how we at VIAVI view the 800 gig ecosystem, we map out the timelines and investment phases of the IC company, the module vendors, DSP, alpha, beta chips going to production, interop, ramping. We follow that through the transponder interconnect and the system vendors. And we look at what their test needs are each stage. So we can deliver that to make sure they can accelerate their product validation, development, and debugging. So today, for 800 gig, the key underpinning technology for the IC companies is 112 gig SerDes. This is the electrical speed that goes between 800 gig chips and modules and systems. Each lane is running at 112 gigabits per second based on PAM4 modulation. So 56 gigabaud PAM4 electrical links. And these links running at such high speeds have the most demanding needs around signal integrity. So understanding every error and the timing margins down below nanoseconds becomes critical. So having a very, very good insight into the physical layer and how it's impacted by signal integrity and timing and skew becomes critical. But also ICs contain very, very complex logical blocks containing millions of logic gates. This can include the FEC, the PCS, and the MAC. Sometimes these IP blocks are coming from third-party companies or may have to be integrated and floor panned inside an FPGA or an ASIC. Again, the validation of this becomes critical. If you don't have your FEC, your forward error correcting code block, working correctly or working intermittently or incorrectly, this can be a very expensive respin of the chip. It's the ability to stress and test these logic blocks to very high degrees over true operating conditions and measuring the margin performance below nanoseconds. That's really what we see as a need from the chip and IC suppliers. Those chips find their way into transponders and interconnect. Even cabling solutions nowadays can become active. So where in the past, DAC cables led the way, we now see not only do we have DAC cables, we also now have active cables, some with retimers, some with linear equalization, all of which to address greater reach with cabling as we move with 112 gig electrical lanes for 800 gigabit. So with the interconnect people, 112 gig signal integrity is huge. Very, very important they understand that, and they get a lot of information from data performance, bit error rate and FEC performance. And we see deep insight into the nature and the fingerprints of errors, and the FEC is critical. We'll cover this a bit later. But also another area that's become very, very important within interconnect is the management, the CMOS aspect. Without that module management, your interconnect isn't very useful because the host doesn't know what it is, the host doesn't know how to control, manage, and orchestrate it. So the software, firmware content of interconnect is very important. The CMOS management and how it works closely, clearly, and concisely with your host is a huge, huge part as well. It's not all about SI at 112 gig and data performance. Without that CMOS module management, the module or interconnect is not very useful. System vendors, again, 112 interoperability and SerDes SI is very critical to them. They're laying out and developing very large boards with multiple plugs and ICs. It's critical that data moves between those ICs, moves over backplanes, moves to front panel plugs very, very well without extra errors, without random signal integrity issues. So margin and stability is critical. The port management plays a big role. As we said earlier, optical modules interconnect have become far more complex with CMOS. It's critical that systems can manage and orchestrate those optical modules and know their capabilities. So we're seeing now a lot more effort going into module management firmware so that host system, a switch, a router, a transport box can fully understand the different plugs plugged into the QSFP DD or OSFP ports and can bring them up correctly and can utilize the wide range of features they might offer. Finally, we see the real use case, the service providers, the ICP labs, the end users. These are the people that really want and need that 800 gig bandwidth. They need to move around that 800 gig bandwidth between systems, either inside a rack or across tens or even hundreds of kilometers for DCI interconnect. So validating that 800 gig service is critical. Performance is king. They must know where every nanosecond goes. They must know what's causing every lost packet, every lost bit. So understanding this, the stability and margin of the system is critical. And of course, interoperability as well. They're pulling together multiple vendors, switch systems, interconnect vendors, companies providing their transport and fiber. All of these must work together for them to move those huge amounts of 800 gig pipes inside the data center, across a network, or even across a continent. So let's look at the whole ecosystem themes at 800 gig, 112 gig SerDes and signal integrity, and understanding the true nature, bit error rate counting, which was very, very successful at 100 gig and below. It's not really applicable anymore to the world of 800 gig because we can have systems with very similar bit error rates, but the true errors, the errors which cause the FEC logic to lose packets, they can be very, very different. So understanding your true error fingerprint, as we'll see later, is very, very important. Interoperability in such an interconnected complex ecosystem remains important. And this is very, very true in the area of CMOS, the module management. And of course, integrating those components on a system in a network remains very, very important. Let's now take a closer look at the challenges leading up the 800 gig wave, the 112 gig SerDes and complex IP we see within the latest generation of ICs. So the fundamental challenge with anyone developing 800 gig class ICs is reliable and stable 112 gig SerDes. That 112 gig SerDes bonds together to deliver your 800 gig data from chip to chip, across the PCB, across connectors. Fully understanding the true nature of the errors there is critical. Of course, those SerDes are coupled at the back with PCS, with FEC, with mat logic. All of that needs to work together and needs to be validated under true conditions with sub-nanosecond precision. Modern SerDes ICs are very, very complex. They are based on lots of DSP, which includes significant firmware content and tuning. So basic BER testing doesn't really help. What's critical to successful 112 gig SerDes, which underpins the 800 gig technology, is understanding the nature of errors. And we at VIAVI have worked very hard to give our customers different ways of looking at the errors. So we're not just counting errors, we're actually getting true insight into the nature and the fingerprint of the error, because with that fingerprint, you can quickly find the root cause and make the necessary changes to board layout or to firmware to deliver a better, more stable product. Optical modules, this is one of my favorite areas. Optical modules at 800 gig, they really are master classes in engineering. Every strong physical challenge comes out, whether it's high-speed electronics, leading-edge photonics, management, thermal integration, it's incredibly challenging. And of course, mechanical integration, getting all these very, very high-performance systems inside a tiny, tiny system, no bigger than your thumb, which is capable of carrying 800 gigabit, and then producing that in large volumes. Well, that really is very, very challenging in every area of engineering. Fortunately, we at VIAVI have very, very good insight into lots and lots of this. We have the ability to look at the electrical domain, the high-speed signals going in and out. All the high-speed signals in that module go over a pluggable edge connector. That's carrying multiple lanes of 112 gigabit per second. It's carrying power. It's carrying control pins to manage the module, the CMOS functionality. All of this goes over a tiny board, a paddle card, and must have the highest measure of signal integrity to give you a reliable product. Inside the module is complex ICs and DSP, equalizing those 112 gig signals, driving lasers, receiving signals from optical domain, converting them into bits. All of these, again, need to be managed and integrated. Those chips need orchestration over the CMOS interface. They need to be integrated and need to meet, again, the exacting signal integrity needs. And of course, there's an optical output. So the photonic domain plays a huge role. Impairments and limitations in the optical domain have an immediate impact on the signals coming out. So being able to reconcile the photonic domain and the errors becomes very, very, again, critical. And of course, luckily, VIAVI have expertise in all of these areas. So if we look today, what matters at 800 gig for your modules, well, it's all about the SerDes, it's understanding the parametric testing, I2C, firmware debugging. All must be done in an orchestrated manner. Having distinct tools, one for the electrical domain, one for the optical domain, one for the CMOS, that's not a good approach. The module is highly integrated, so test tools need to be the same, because any changes with CMOS immediately might impact optically or electrical domains and vice versa. So having integrated solutions to these very integrated modules, that's the best approach from moving very quickly from the R&D to stable and good alpha samples, which our customers are very keen to work with, through to beta and production. And beta and production is very important because you need to have very high yield, low touch production in optical modules. Network equipment manufacturers at 800 gig. Well, of course, the network equipment manufacturers, they're bringing together and orchestrating complex ICs, pluggable optics, like QSFP, DD800, OSFP, or even cables, and of course lots of software and firmware to control and manage the modules and ICs. That all comes together to deliver network elements that deliver those terabits of bandwidth with nanosecond precision, because people just don't want the bandwidth, they need that bandwidth in a consistent manner with stable and predictable latency. All of this needs to happen. Of course, it's all underpinned in interoperability. People will interoperate their equipment from multiple vendors, and it needs to be based on standards. So people who understand the standards and contribute to the standards and are involved with the standards, like VIAVI, we've got the deeper insight into what matters to on a good, stable interoperable product. There's a huge range of interconnects that the network equipment manufacturers need to deal with. Everything from short DAC cables, perhaps a meter, which go between inside a rack, to long haul 80 kilometers plus coherent optical modules using complex modulation across optical DWM networks. All of these must come together. And remember, those modules and those interconnects can be delivering huge amounts of data back into the host that needs to be orchestrated. Performance monitoring data on optical signal to noise, DAC cables reporting states of equalizers and eye scans. All of these need to be managed as well. It's not just about the 800 gig data and the 112 gig SerDes. It's closely orchestrated with the module and interconnect management like CMOS. Multi-domain visibility is really the only way to approach this successfully. Trying to look at one set of problems in the module management domain and then moving over to the 112 gig SerDes domain, then moving into the packet domain, the optical domain, very, very challenging, because the reality is they're all tightly interconnected in the functionality of the silicon and of the modules. So getting a view on the 112 gig SerDes, module orchestration, firmware, CMOS, and even the photonic domain, that's key to understanding and developing and debugging those network elements very, very quickly and, of course, successfully. The operator onion. Let's peel back the challenges there. So operators are deploying systems, today 400 gig and some 800 gig, in very, very high volumes. They want to deploy 800 gig services quickly and trouble-free. They need the speed and the bandwidth. They don't want the hassle. They don't want interconnect issues, interop issues, bit errors causing link flaps on a Friday afternoon. They want to deploy 800 gig services reliably, quickly, cost effectively at huge scale. They bring together many, many elements: servers, switches, interconnects. All of these must work seamlessly together. And if they don't, that's a big problem. In fact, the worst case is if they nearly work, but they haven't really been stressed or margined. So they put it together, the initial turn-up test looks good, then we have these random issues that perhaps only occur once a week on a Friday afternoon. Having the insight and tools to stress and debug becomes critical, whether it's inside the data centers, the connection between switches and servers with DAC cables or breakout, interoperability with vendor, speed and latency become critical. Remember, inside the data center, your data packets will be crossing multiple interconnects. Those DAC cables, those active optical cables, for every process you want, they will be pinged backwards and forwards tens of thousands of times of data. So the impact of a bad system, a few nanoseconds here or there, becomes critical. Tracking every nanosecond becomes critical, because even though it seems like 1 or 2 nanoseconds inside the module or the switch, when you multiply that with the tens of millions of times a second, those packets cross silicon, backplanes, systems, modules, it quickly adds up, and it quickly has a real cost to the operator. And of course, across the data centers, that becomes a very critical issue as well. Data centers nowadays are huge, and they're growing with the bandwidth needs. So DCI, data center interconnect, is a very important topic. It started at 400 gig. It's going to be a huge topic with 800 gig ZR. Those coherent optics moving bandwidth between data centers effectively over fiber is very, very important. They're very complex. They have tight interaction between the optical domain, the data domain, and management. And understanding the puts and takes there is very, very critical. And we see one of the biggest challenges with DCI isn't just the high-speed 112 gig performance of the SerDes, or indeed the very complex optical modulation, but actually the module management with the coherent CMOS, understanding how to pull off data reliably and how to use that data in conjunction with the real physical state of the electrical domain, the optical domain. That's critical to understanding as an operator what's really going on in your network, and is your network got enough margin to operate successfully under duress for a long time. We at VIAVI have a lot of experience. Ethernet is already 50 years old this year. Many of you may have seen some activities with the Ethernet Alliance, and we at VIAVI have been developing Ethernet products for much of that time. We also have a lot of experience in the PHY layer as well. We bring all of this together because, as we've talked about already, you need to look at multiple domains to debug our chips to systems ecosystems. This experience of chips to systems comes together in our VIAVI ONT range. The product for 800 gig, we call it the VIAVI ONT XPM module. And this really is a true chips to system solution for 800 gig. We support a variety of form factors out there, whether it's QSFP DD800 or OSFP 800. We work all the way up to 800 gig traffic, supporting both the Ethernet Technology Consortium and the IEEE DF flavors of Ethernet, but also we understand that many people today are deploying 800 gig as 8 times 100 gig high density or 2 by 400 gig. In fact, as of today, still many of our customers working on 800 gig technology are actually deploying the systems as a dual port 400 gig high density. We have all the tools built in, covering from the PHY layer, like our unique dynamic skew, through stressing IP blocks like the FEC stress tool, coupled with our unique transponder track-all language for managing the CMOS. So this system really is a true chips to systems approach for testing. Whether you're there very early on in the IC development, going through to developing IP like FEC, bringing to market modules for 800 gig, or testing and setting up a system, the ONT FLEX XPM module is the ideal solution. It's true chips to systems coverage for the 800 gig needs today, from the deepest PHY layer all the way through to 800 gig services measured with nanosecond precision. So let's have a quick overview of what the ONT 800 we can do for you at 800 gig with the ONT XPM. On the right-hand side, we show a typical screenshot from our ONT. This is at a glance view of the 800 gig receive stack. You can see great detail, everything from the 32 logical PCS lanes through the skew. You can see how hard each of the FEC blocks working. 800 gig technology uses 4 interleave FECs. The VIAVI, you have deep insight. You can dive down into each of those FEC blocks and fully stress and validate it. And you can see all the way through the stack what's going on from the physical layer, PCS layer, MAC IP layer. Immediately you can see what's going on at each layer and the performance of each layer, because as we've mentioned many times, they're very, very tightly interlinked. The physical layer impacts the PCS layer, impacts the MAC layer. And of course, at the MAC layer, where those packets need to come with nanosecond precision, that can be definitely impacted by what's going on in the FEC and what's going on in the PCS layer. So true multi-domain visibility is critical. We also see it's not all about just looking at what's going on, it's also about stressing things. One of the key advantages of the VIAVI product line is we have lots of tools to actually deliberately cause issues of transmission. These stressors, which can range from injecting bit errors or stressing particular words and lines on the FEC, through to deep down in the file layer, dynamic skew or frequency variation, are absolutely critical. Because what you need to know when you bring your product to market, not only under normal conditions it works, but what about error conditions when there's stress, when there's frequency variation in the ppm offset, when there's lane skew which can occur over time and temperature? What happens when there's errors? Does your logic, does your system behave correctly? So with the VIAVI, we can inject all the range of errors from the deepest file layer up through to the MAC and IP layer, and you can have the confidence that your chip, your module, your system behaves correctly, reports the errors, perhaps over CMOS or over the management interface, and takes the right action. All of this can be done at all the Ethernet speeds from 100 gig to 800 gig with nanosecond precision, supporting all the flavors of optics from QSFP DD800 through to OSFP 800, and we're also ready for the latest generation of coherent modules. Many of those modules very early on in their life cycle can be over 30 watts, but with the VIAVI experience in cooling and thermal management, you have the confidence that your module will work inside our systems, be cooled and managed, and be delivered stable power so you can focus on the testing down in the file layer in the nanosecond domain. We've fully integrated debug tools so you can have full confidence and visibility of the CMOS module management interface as you vary the key parameters and bit errors under your control. So let's summarize this. 800 gig is the next module bandwidth and the Ethernet rate. Early deployments using 800 gigs typically are using this as 2x400 gig breakout. Both OSFP 800 and QSFP DD 800 form factors are being used today, and we are beginning to see now the early stages of 800 gigabit Ethernet turn up, and it's going to interop and validation. VIAVI has been closely involved with several public interops, including large vendors like Intel at OFC. We are leading the way supporting companies developing 800 gig ZR and LR coherent systems. The VIAVI ONT XPM has been used across the full ecosystem for full test immersion coverage, from the signal integrity challenges of those 100 gig SerDes through to validation of the IP, the 4 ledge effect blocks inside 800 gig. We can do that with sub-nanosecond latency and precision. So we have full visibility as we go from chips to systems with your partner VIAVI. I'll hand back now to Kenneth, and we're ready now for taking your questions or any other themes you'd like to address. Thank you.
Thank you, Paul. If you have any question, put onto the Q&A. I got the first question. Why can't the BERT test help find the issues at 112 gig?
Yeah, thank you, Kenneth. Actually, I was sort of expecting that question. That's a question we get a lot from people we engage with. So traditionally, people want to look at the BER. They're very familiar with that because that's something that was quite useful, back in the days of NRZ before we had PAM4. The challenge is, of course, that errors are always there now with the PAM4 links, but a BERT test is too coarse and just counts the errors. It doesn't really give you the details on what's really going on. So you don't know if these errors are associated with a particular PAM4 level. You don't know if these errors are bursty or bit slips or anything else. We at VIAVI worked very closely with a range of customers when they first brought to market their PAM4 chips. It was pretty clear what they needed to understand was, were the errors coming from SI issues, which might have random noise distributions? Do the errors have burstiness, which might be caused by major crosstalk issues, logic issues, or are they bit slips? So where whole lanes have moved over, that can be caused by bad timing CDR issues. They need to know this very quickly so they can make the right adjustments in their chips and systems. So we at VIAVI developed a range of tools which don't just simply count errors or count zeros and ones. They actually tell you, is this a bit slip? Is it a burst of errors? Which lane did it occur on? Which PAM4 transition did it occur on? So immediately people troubleshooting can understand where things are going wrong. And critically, this is also done with framed traffic, because we now know that many of the ICs people develop don't really work with PAM4 signals, PRBSs. They work with live traffic because it's got to cross the fabric and things inside backplanes and chips. So having the ability to look at these errors with live traffic is really key, because in some cases you may not be controlling the far end, you may be debugging a system and it might be only able to send live Ethernet traffic. So the ability to look at the errors with that's very, very important. So we've developed lots of tools that give you far more insight and detail, which is critical for troubleshooting and debugging, than a very, very basic BER can do. So I hope that answers the question.
Yeah, thank you very much. Very clear. And then the second question is, what is FEC stress test, the forward error correction stress test? What is it?
Okay, that's a good question. So the FEC, the forward error correcting coding, is a very important part of 400 gig and 800 gig Ethernet. Because the data is now going so fast on 50 gig or 112 gig PAM4 lanes, there'll always be some errors. So on transmission, the data is taken and there's some extra calculations have done to create extra data, which allows at the far end the data to be checked and corrected. This is called the FEC process, forward error correcting. Now, the FEC logic at the receiver is very, very complex, and it needs to work very quickly with low latency and very high performance. Often this logic IP block may come from a third party. So companies need to integrate this inside their chip or their FPGA. And we found in the early stages of 400 gig, this was a problem area for many groups of people. They might get FEC that worked logically okay, but under low conditions, there was issues. So we created a suite of tools we called FEC stress tests. FEC stress test is a very precise tool that deliberately and methodically creates certain error fingerprints, which then stress the FEC logic at the receiver in a very special way. We can then inject very controlled amounts of errors in a very precise manner, which stresses the FEC logic, so the end user can determine many things. First of all, they can determine if the IP block they've bought and integrated is operating correctly. Is it compliant with the standards, with interoperability in compliance to 802.3, etc. That's very, very important. The second point is they can understand under load conditions, when errors are injected, can their management software determine the error rate? Okay, so they know they're getting 3, 4, 5, 6 errored symbols in each code word, because when you get to 16 errored symbol in a given code word, you can no longer correct the error. You start dropping packets. So it's very important to understand how you behave there as well. And finally, the logic of a FEC is very, very dynamic in its nature. So the more errors you get a very different power profile. The power integrity of the logic block is very, very important. So we've also developed unique tools which help people understand the robustness of their power integrity solutions around the FEC block. That can include how good their point of load power supply converters are near the IC, the decoupling capacitors near the packaging. All of these play a role. Even where that FEC logic is floor planned inside the IC, that can all have a huge impact in power integrity. You may have a logical FEC block that is technically correct, but because of lack of attention paid to the power integrity, the FEC block can fail under certain conditions. So the FEC stress test measurement suite allows users to fully test the logic under all conditions, and after this test they'll have the confidence that the logic is correct, the management system can read and understand errors correctly, and of course they have a stable implementation that will work under all power conditions. So this is very important, and we do work very closely with many companies, especially in the IC space and the NEM space, network equipment space, to help support their integration with our FEC stress tools. Okay.
Then the last question I have is, when do we get the 800 gig ZR modules? I guess it's the when is it available, right?
Yeah, that's a good question. So we've seen a lot of interest in this technology. 800 gig ZR is the next wave of pluggable coherent optics. So many of you have seen at many trade shows, including the OFC and ECOG shows, multiple vendors showing 400 gig pluggable coherent optics in both OSFP and QSFP DD form factors. We at VIAVI have worked very closely with leading edge companies developing the 800 gig coherent DSP and the module integrators, and we've actually already worked with them and had some demonstrations of 800 gig ZR technology. So I think that technology is emerging now. We at VIAVI are prepared to support that, and we do believe that come the OFC show early next spring, we will see multiple vendors demonstrating interoperability between 800 gig ZR solutions over 80-kilometer links with very, very good success. This technology is definitely emerging, but there's already a healthy ecosystem of coherent DSP and module vendors all ready to bring and develop products to market. And we're very proud to say that VIAVI is playing a very big role in helping and enabling this ecosystem.
Thank you for joining today's webinar.